All right, everyone, we're going to start the next unit with this lesson, and we're going to talk about the definition of derivative here to kind of get into our whole derivatives unit. So first and foremost, what is a derivative? Well, derivatives give the slope of the line tangent to a function at a single point, at the point x equals a. This is also known as the instantaneous rate of change of the function at x equals a. So suppose we have some function like we do here in purple, and I've got some x value I'm calling a. Here's the y value associated with it. We'll call that f of a. Just function notation for the y value at a. And basically, you know, as we look at this function, if we were to draw the tangent line at that point, we can see that that tangent line has some positive slope the way we've drawn that. Well, whatever the slope of the tangent line is right there is what we call the instantaneous rate of change of the function. That's the rate at which this function's changing at that single point. So how do we find that? Okay. Well, let's take a look at how we can find the slope of a function at a single point. Now, recall, typically slope is given by, if you have two coordinates, change in y over change in x. Sometimes we write that as y2 minus y1 over x2 minus x1. If I'm using function notation, instead of writing y2, I could write f of x1. It's the same thing. That's the y value for x1. Let me use 2 as a subscript first. So there's the y value for x2 minus the y value for x1 over x2 minus x1. Again, this is just function notation for the slope formula. Problem with using the slope formula at a single point is the following, right? Basically, I have a single point here, a comma f of a. All right, there's the x value and the y value. If I try to find the slope using that same point twice, well, if I sub the same y value in and I sub the same x value in, this thing approaches 0 over 0, which, as we saw in the land of limits, is typically undefined. Okay, or more precisely, it's indeterminate form, right? So that's the problem with taking the slope at the same point, is that you're always going to get this indeterminate form of 0 over 0 back. You have the same numbers in the numerator you're subtracting, same numbers in the denominator, okay? So obviously, the way we've drawn this, there is some slope. It is going to be defined by some number, particularly a positive one in this case. How do we go about doing it, okay? Well, the idea is this, okay? Let's back off of the tangent line for just a minute. And let's take a point nearby, okay? So maybe I pick up this guy right here that I'm just going to call x sub 2 or something, okay? If I find that y value, there's f of x sub 2. And now what I can do is draw a line connecting these 2 points, all right? This is called a secant line because it goes through 2 points. A tangent line would just touch at 1 point. Now, as you look at the slope of the secant line and compare that to the slope of the tangent line, they're not perfectly the same. Okay, they're not exactly the same. So what we can do to try and get a little bit better of a slope is let's actually move this x2 value a little closer to a and see what happens here. All right, so I'm going to bring this guy a little bit closer to a. Maybe I get it right here. Now here's my f of x2, and when I draw this secant line in, it's going to have a slope a little closer to the slope of the green line. And in fact, I can do even better if I bring x2 even closer to a. Whoops, I don't want to erase the entire thing there. If I bring this one point a little bit closer so that they're basically right on top of each other, and I draw the secant line, now we're going to have something that's getting closer and closer to the slope of the tangent line. Okay, so basically the idea is this: the closer we can bring this point to A, the better job the slope of the secant line will do at approximating the slope of the tangent line, which is the value we want. Well, what are we doing when we're taking this x value and bringing it closer to A? Well, we're just taking the limit, right, as x approaches A. And this is where the definition of derivative comes from. Okay, basically the slope of f at x equals a is given by the limit as this thing I'm going to call x approaches the number a, and change in y over change in x. So again, as x approaches a, we're going to get f of a minus f of a over a minus a, which is 0 over 0. It always starts in indeterminate form, but by letting this get closer and closer to that, we should be able to evaluate this limit analytically, and we'll be able to get the slope of the tangent line back. And that's the idea behind the definition of derivative. Okay, I think you guys in pre-calc may have seen a definition that uses the letter h approaching 0. We'll talk a little bit more about that a little later in this lesson. I'll tie the two together. Okay, but to me, this is the most intuitive way to really understand the idea of a derivative. We're looking for the slope at a single point. You can't really use the slope formula at a single point, so we basically take the limit as x gets really close to a, and again, this is slope, change in y over change of x. And this is how we specifically determine a derivative at a point x equals a. Okay, so here, definition of derivative at x equals a. This is the same exact formula. F prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. This will give the instantaneous rate of change of the function at a. It will give us the slope of the line tangent at that point. Sometimes we're going to be interested in what I call the general derivative, okay? Not necessarily like the derivative at a point, but just in general the derivative. So you may remember from last year, like if I have f of x equals x squared, you could probably remember from last year to take the derivative, you're going to bring down the power and reduce by 1, okay? This is what I call the general derivative, okay? Versus evaluating at a point, like if I want f prime of 3, 2 times 3 is 6. So the difference is this is the slope of x squared at x equals 3. This is the general derivative of x squared at any x value for which it's defined. Okay, we're going to practice these things. But in any event, if you notice in green, I have the general derivative formula. Instead of f prime of a, we want f prime of x. So we want our answer to come back in terms of x. And it's more or less the same thing here. We do have change in y over change in x for all intents and purposes, our slope formula, just like up here. But the big difference being that we now have some placeholder value we're calling t. Don't overthink it. It's going to be replaced by the letter x at the end of the day, and we're going to get our general derivative. So let's see how these formulas work. So in WebAssign, there's a couple problems that are going to say, use the limit definition to take the derivative, and this is where you get to practice taking derivatives using the definition of derivative, like we're about to. Typically, this is not how we're going to be taking derivatives. This is kind of like a one-day thing, just to see how it's done. Starting after the next lesson, we'll be learning little formulas and algorithms for taking derivatives. Kind of like, you know, oh, like we said, the derivative here is going to be 2x, right? We'll start doing that kind of quick derivative tomorrow. But for now, you know, if you remember from pre-calc how to do this, we can kind of figure out what the answer is going to be before we start the problem, which can be good for checking if we're right. So in any event, find f prime of 3 if f of x is x squared. Okay, so we're basically looking, what is the slope of x squared at x equals 3? Well, believe it or not, we actually kind of just did that up here. Let me illustrate this. Okay, so this question is asking us find f prime of 3, the slope of x squared at x equals 3. So if we're looking at x squared, our parabola, and I'm calling this x equals 3, I'm looking for the slope of this at 3. And again, using, you know, some techniques from last year, if f is x squared, f prime is 2x. If I want to evaluate this at 3, well, 2 times 3 is 6. And so what we're showing is that this tangent line, or the function itself, has a slope of 6 when x equals 3. And that seems reasonable the way this is drawn. Okay, but how do we actually use the definition of derivative to do that? Well, first thing we're going to do is decide which of these forms are we going to use. Here, we want f prime of a value, so we're going to use this top form at x equals a. So in this problem, it's kind of like the number 3 is our value of a here. Okay, so look, we've got f prime of x, a equals limit as x approaches a, f of x minus f of a over x minus a. Okay, so first thing I'm going to do is replace a with the number 3. So anywhere I see the letter a, I'm going to replace that with the number 3 here. So f prime of 3, it's going to be the limit as x approaches 3 of f of x minus f of 3 over x minus 3. So there's our setup. Now what we do is we actually are going to evaluate the numerator. We're going to clean these two things up, okay? What is f of x in this problem? Well, it's x squared, so I can replace f of x in my numerator with what it is, x squared. What would f of 3 be? That's the next thing I need up in the numerator. Well, f of 3 is going to be 3 squared, right? And so that's 9. So we actually evaluate the function in the numerator, leave the denominator alone for a minute. And now you should pretty much realize, hey, this is where if I actually plug 3 in, we're getting back 0 over 0. And that should basically happen every time we get this indeterminate form. At this point, based on the work we did last unit, you should kind of recognize where we need to go to evaluate this. We're going to simplify it. And when the x minus 3's cancel after factoring, we'll just be left with an x plus 3 in the numerator. And now when I reevaluate, 3 plus 3 is indeed 6. And we got back exactly what we had anticipated. Okay, so this is using the limit definition. Okay, replace a with the number it equals, replace the functions in the numerator. One is f of x, one is f of the value. Then deal with the indeterminate form. Okay, next example. Now we're looking for a general derivative. Find f prime of x if f of x is x cubed. Okay, and again, off on the side, if you remember from last year, and I'll reteach you this rule tomorrow, but as far as today's goes, we focus on the definition derivative. But if you remember, look, here's our answer. We know this is what we should get back at the end of the day. So again, here I want f prime of x, so I want the general derivative. So I'm going to use that green one we saw up above. F prime of x is the limit as t approaches x, f of t minus f of x over t minus x. We don't have to worry about replacing x with any number here, okay? Similarly to the last ones, the focus right now is going to be up in the numerator. So I'm going to evaluate f of t and f of x. Well, if I replace x with the letter t, we simply get t cubed here. So it looks like f prime of x is going to be the limit as t approaches x of t cubed, that was our f of t, minus f of x, which it is x cubed, over t minus x. So we've subbed in for the functions in the numerator. If I was to replace the letter t with the letter x now, I would be getting back 0 over 0. Again, pretty indicative of definition of derivative limits, okay? Well, again, we do have, difference of perfect cubes in our numerator. This is something we can factor. And that would be t minus x, t squared, plus t times x, plus x squared. Over, and now we can simplify this. And now I can evaluate the limit. So again, I'm replacing all the letter t's with the letter x here. And let's see what we get here. Well, that's going to be an x squared. In the middle, we're going to have x times x is another x squared. And at the end, we just have an x squared. That's not dependent on what t does. And so if we add it all up, we're going to have x squared plus x squared plus x squared, which is indeed 3x squared, as we imagined. Okay. And bear with me for just a sec. Okay, so it's just kind of skipped out for a minute there, but here's the rest of the work. So again, replacing with x, we get x squared, x times x is another x squared, and then that's just x squared. And sure enough, as we had anticipated, 3x squared is the end result here. Okay. Okay. So now let's take a look at this other form of definition derivative that perhaps is a little more familiar. I think that this is what they use in pre-calc, okay? So we're going to take our definition of derivative and we're going to transform it into this h1. And you may recall that where would you see h? In the denominator. So what I'm going to do to get started here is I'm going to let the denominator h equal x minus a, okay? And from this, we're going to rebuild our limit. Okay, so basically my job now is to take anything that's in terms of x, and I got to figure out what that entails for h. Okay, so the job is I'm going to get rid of anything with an x in it, and I'm going to turn it into something with an h now. Okay, well, let's see. Up here we have f of a. Okay, that doesn't have an x in it, so I'm actually going to leave that guy alone. This f of x has an x in it. Okay, so here's what I'm going to do. I want to see what is x in terms of h. So I'm going to come back over here where I have x equals a minus h. And if I wanted to get the letter x by itself, what would I have to do here? Well, add the a, right? So I can say x is equal to a plus h. All I did was add the a over. So f of x becomes f of a plus h. And the only other place we see the x is in the limit. So basically what we want to do is figure out, as x gets closer to the number a, what is h doing? Well, let's think about that. As this number x gets closer and closer to that number a, what is that difference, which equals h, going to get closer to? Well, the closer x and a are together, the closer that difference is to 0. So as x approaches a, h is approaching 0. That difference approaches 0. And now here is probably, again, a more familiar looking version of the definition of derivative. It's just an algebraic manipulation of the original definition. Okay. And we call this the difference quotient. That's just the fancy name for this particular form. And once again, I have here's f prime of a version. This is the instantaneous rate of change. Whereas down below, here's the general derivative for f prime of x. Okay, so again, let's just practice taking a couple derivatives using this in terms of your homework. I really don't care which form you use. That's completely up to you. You just got to be aware of these things, okay? All right, so here we want f prime of x if the f of x is the square root of x. Okay, so we're taking the general derivative. We're going to be using this form right here. We just want f prime of x. Okay, now again, kind of known going in, if I wanted to figure out what the derivative of this was, I'd probably rewrite it as x to the 1/2 power. Now I can take the derivative, bring down the power, subtract 1, and with that negative exponent, that's going to put x under a square root in the denominator. So again, this is kind of what we expect the answer to be if we're just using our basic power rule formula that you learned last year. Okay, but let's go through the algebra. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. And it's very similar to the other form. Here we're going to replace f of x plus h and f of x in the numerator with what we're working with in this problem. So here we're going to have the limit as h approaches 0. Now, f of x is radical x. All right, so we're going to have minus radical x right there when I replace f of x with what it equals. F of x plus h means I'm just going to replace x with x plus h. And so we literally get back radical x plus h here. Okay, now again, as you look, if I were to actually replace the letter h with 0, this thing's going to come back 0 over 0, which would be indeterminate form. And typically this is like going to happen every time we do a definition of derivative limit. So again, we need to get through it. Well, hopefully you're realizing there's nothing to factor here. We're probably looking at using binomial conjugates to clean this thing up. So here I'm going to use radical x plus h plus radical x on top and bottom. Okay. And the original radical was in the numerator, so I'm going to distribute this out. So we're looking at limit as h approaches 0. Okay, multiplying these together is just going to be x plus h. The outer and the inner will cancel, as conjugates do. When I do negative radical x times positive radical x, we just get minus x. The denominator I'm going to leave factored. I'm not going to distribute that out because I anticipate some cancellation occurring here, okay? So there's that. The x's in the numerator cancel. I'm now left with h over h times this quantity. The h's cancel, leaving me with a 1 in my numerator. So if I clean this up just a little bit, we're now looking at something like this. Once you simplify, you can now evaluate the limit. Well, radical x plus 0 is just radical x. And add a couple radical x's in the denominator to get 2 radical x's down there, as we had anticipated. All right, so again, a 0 over 0 limit is what resulted, taking the derivative, and we cleaned it up using binomial conjugates. Okay. Be aware of ways questions can be asked. Find the rate of change of f at x equals -2 if f of x is 1 over x. Find the rate of change. We are being told to take the derivative. Okay, and we are specifically looking for f prime of -2 here. So we want f prime of negative 2 here. Again, if I kind of want to do some work on the side, if f is 1 over x, I'm going to rewrite that as x to the negative first power. Taking the derivative, bringing down the negative 1, and subtracting, we get negative 1 over x squared. If I was to evaluate this now at negative 2, we're going to end up with negative 1/4. So this is what I anticipate our answer being. Okay, but again, let's go through the definition of derivative to do it. So, f prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h. Here we have a value for a, negative 2. So I'm going to replace a with negative 2. Okay, now we're going to evaluate these functions. F of negative 2 plus h. If I replace x with negative 2 plus h, I get 1 over negative 2 plus h. Minus f of negative 2, 1 over negative 2. And then h in our denominator. Now I'm going to clean this up just a little bit. Notice this can be written a little more neatly as h minus 2. And certainly the double negative here will give us a plus 1/2. Okay, if I was to again replace the letter h with 0, I'm going to get 0 over 0 here. Okay. Well, we're not worried about binomial conjugates here, and there's really not a lot to factor here, so this requires just a little bit different of a technique. I'm actually going to go ahead and try to clean the numerator up by getting common denominator. So I'm going to actually multiply this by 2 over 2, and I'm going to multiply this by h minus 2 over h minus 2. And now we will have a common denominator up in our numerator. So I'm going to have 2 over 2 quantity h minus 2 plus h minus 2 over quantity 2 times h minus 2 all over h. So I just clean that up right there. Now that I have a common denominator up here, I'm going to put that together. So we're going to have 2 plus h minus 2 over the common denominator all over the h. And let's see, those go. I'm going to do this just to help you see the algebra a little better. I'm going to make that h over 1, and I'm going to do keep change flip. So we have h over 2 quantity h minus 2 times 1 over h, and there go the h's. So we now are left with the limit as h approaches 0, 1 over 2 quantity h minus 2. And look at what we get if we replace h with 0 here. 1 over 2 times negative 2 is indeed negative 1/4 as we had anticipated. Okay. And maybe one more just to see how it's done with multiple terms, just being careful. Find the general derivative f prime of x if we're given 3x squared minus x. And again, if you remember the easy way to do it, we would anticipate this being our answer, 6x minus 1. Okay, so here we go. Limit as h approaches 0. F of x plus h minus f of x all over h. Okay, f of x plus h, I replace x's with x plus h's. So 3 quantity x plus h squared minus the quantity x plus h, notice my use of parentheses. That was this. Now I have to subtract f of x, which is this whole thing. So I'm going to subtract the whole quantity of f of x. So again, just be careful with your parentheses, take your time. Okay, and again, a little bit of cleanup work here, following the order of operations. First thing I'm going to do is actually square this out. If you try to plug 0 in for h now, you're going to get 0 over 0. So let me square that out. We'll get x squared plus 2xh plus h squared. And now I'm just going to go ahead and distribute my 3 and my negatives here. And let's see what happens. So we're going to get 3x squared plus 6xh plus 3h squared minus x minus h minus 3x squared plus x all over h. And now let's kind of go through and see what happens here, right? Notice we have a 3x squared with a minus 3x squared. They're going to cancel out. We have a minus x with a plus x. They're going to cancel out. Okay? And in fact, anything that's just in terms of x ended up canceling out here. Every single term that's left has still got the letter h in it. So cleaning this up, let's see. We've got 6xh plus 3h squared minus h all over h. Well, we can certainly factor this to get around 0 over 0. I can factor the h out of the numerator. And now we get the cancellation. Now I can replace the letter h with 0. And what are we going to get back? Well, 6x isn't affected. 3 times 0 is 0. The minus 1 isn't affected. And sure enough, there's the derivative as we kind of anticipated. Okay, folks, so this is a definition of derivative. Beginning tomorrow, after tomorrow's lessons, we're going to be learning algorithms, and we'll be taking derivatives like I did kind of up here, doing it quickly. All right, but this is, in essence, the way we take derivatives. You know, bringing down the power and subtracting from 1 is just a convenient result of limits that, if you still did it this way, would still come out the same. All right, if you have any questions, let me know. More to come. Have a great day.